We're sort of very ambitiously targeting a 2031 launch window, which would be kind of our first demonstration of ISRU with a couple different options there for how far we get. It's like, do we just grow something on Martian resources? Do we grow something on Martian resources and then make something useful and then purify it? Or do we try to go all the distance and like we sort of have this design that we've scoped out for how you could use biology to create, we're thinking like these kinds of bioplastics or maybe a cellulose aerogel. And then like using 100% Martian resources, so it's technically like you can make an infinite amount of it as long as you just keep running the bioreactor, and then use that to create like a passively heated greenhouse on Mars that can create sort of a habitable environment.
Welcome to Galaxy Balance. Galaxy Balance is a conversation series about the frontier, the place where biology, technology, and imagination meet. Each episode explores how the tools we build today reshape what becomes possible tomorrow, whether in the lab, in society, or out among the stars. We talk to scientists, founders, engineers, and thinkers who are expanding the edges of knowledge and challenging out assumptions about the future. Today's guest is Devon Stork, a synthetic biologist who specializes in engineering non-model bacteria and expanding the fundamental genetic and biochemical capabilities of life. Devin studies chemistry and biology at Harvey Mudd College, graduating with high distinction, and then earned his PhD at Harvard University with George Church and Ethan Gardner, where he helped push the limits of genetic code expansion in Bacillus subtilis, including work published in Nature Communications, Nature Chemical Biology, and PNAS. In industry, Devin has worked at the cutting edge of probiotic therapeutics, building synthetic biology platforms in non-model, gut-resident organisms, and developing these strains for manufacturing and drug delivery. He's now part of the founding team of Pioneer Labs, a non-profit research institute advancing biotechnology for use in space. Everything from microbial chassis species for extraterrestrial environments to long-term biomanufacturing off Earth. Beyond the lab, Devin is also a writer, the author of a published fantasy series, an active blogger on evolvability and engineering principles in biology, and a key contributor to Pioneer's public science writing. Devin brings together deep technical expertise, creativity, and a willingness to explore speculative frontiers. Devin, welcome to Galaxy Balance.
Thanks, Corey. It's good to be here. It's nice to talk to you again. It's been a few years.
Yeah, it's great to talk, and I've been talking with a bunch of ex-Church Lab members, so hopefully this can connect us all through this series. Well, I wanted to start off with your most recent venture into Pioneer Labs. If you could talk a little bit about what motivated you into founding Pioneer Labs, and what gaps you think this fills in the landscape of space-focused research.
Yeah, I mean, there's a lot of ways to answer that question, but Pioneer Labs is really kind of, it's one of these, it was inspired by these focused research organizations, these sort of nonprofit science initiatives that look for philanthropic money in order to go after problems that aren't quite suited for industry or for academia. And our focus here is really this idea that there's all this really cool science that needs to be done to prepare biotechnology to work in space, basically. And it's not really happening because it's a little bit large scale and requires sort of a many-year sustained effort, but it also doesn't initially have a profit motive. So a lot of what we do is think about what technologies we can develop to sort of create the field of space synthetic biology or really biology in space that can be functional and help astronauts sort of in the near future and then sort of extending off into the farther future. And the exact details of what we're working on has evolved a lot over time. We were sort of ideating back a few years ago, and it was very much like, okay, what bioreactor designs can we start designing microbes for? And it was like, wait a second, that's like way too far down the pipeline. We need to take a bunch of steps back. Those bioreactors don't exist yet. And a lot of the problem is that they don't even know what kind of bacteria they would put in them or what requirements they have. And then we kind of did a lot of research and we're like, wait, all of this biomanufacturing that exists on Earth now requires this crazy amount of infrastructure. You need to balance the pH and the oxygenation and the the acidity, and all of these other things in order to get something efficient. But all of that infrastructure gets exponentially more expensive in space. And so if anything, I would say the best summary of what we're doing now is trying to make chassis organisms that require less babysitting to be productive so that you can use them without as much infrastructure.
Yeah, and it seems that, at least on Earth, the development of E. coli has been a chassis system for most genetic manipulation, but you're right, it still has very tight growth conditions and parameters, clearly not suitable for space. Who are the leading contenders for your chassis organism at this point?
We've got a couple. We spent a long time, actually. We at first thought it would be, it's fairly simple. Let's design a little extraterrestrial environment that we can then screen bacteria through to find some good ones. And that process actually took a very long time. We ended up focusing on Mars, which is a pretty popular target for this sort of, it's called in situ resource utilization, or ISRU development. And we built a media out that was what you'd get if you took 40 grams of Martian regolith and mixed it with a liter of water, and that's your inorganic nutrients. And then you're adding acetate or acetic acid as your carbon source, because you can make that electrochemically from carbon dioxide, water, and electricity. And so we screened through a bunch of organisms to figure out which ones could grow decently in that. And we actually ended up with two fairly commonly used biomanufacturing organisms, C. nicotter and P. putida, which are both like being actively developed as sort of frontier, very commonly, or like on the edge of what is considered good biomanufacturing organisms.
And a fascinating concept of in situ resource utilization. I think that's key for whatever space travel we go to. What other places were you evaluating? I imagine low Earth orbit, the moon, Mars. What made Mars the front winner for you to focus your first research on?
Yeah, we did a fair amount of exploration here. The problem with things that are orbital or in space is like you're not able to get mass from other places. You sort of only have what you bring with you. And in that case, what you're talking about is like a closed circuit life support system, which is interesting, and there are developments going on there. But a lot of that is sort of more like a very mechanical engineering focus, with biology as very key modules that we didn't feel the best suited to really tackle. So we were more thinking about this, like, how do we take molecules from these other places that we might go to and turn them into something useful. And so we did actually some pretty detailed elemental profiling on various places in the solar system. The moon is a problem because it has very little carbon and nitrogen. There's almost no nitrogen, and to like grow a tree, you need to excavate something like a cubic kilometer of Martian regolith to get enough nitrogen. And that's assuming like 100% recovery rate. So that didn't seem like a super good potential option. There's a little bit more in the shadowed volatiles, but it's not a lot, and there's other issues there. Mars is appealing because it does have all of those ingredients. There's a lot more regolith there's a lot more nitrogen in the regolith. There's abundant carbon dioxide in the atmosphere, and a good deal of nitrogen as well. So all of the ingredients for life are present on Mars. The outer planets are also pretty interesting. The problem is that they just take so long to get to. Like, if it takes you 3 months to get to Mars, it takes you 7 years to get to any of the gas giants. So while some of the moons there do have all of the necessary ingredients, they're just so much harder to get to that it seems like not a very good first place to focus. There's also some interest in asteroids in various directions. One of our collaborators likes this idea of sort of throwing a giant plastic bubble around an asteroid and using solar heating to turn it into something like an actual little bubble of life. Because those do have all of the necessary ingredients. There's a lot of ammonia and water and other nutrients there that actually probably are a complete mix for everything you need to grow life.
That's fascinating, and those outer planets are very interesting. I asked George which of his on the podcast, which place in the solar system do you think is most likely to find life? Similar to yours, what's suitable to have life? Set aside the travel distance or the time. What do you think is the best planet or moon or area in the solar system that's suitable for life, or we're likely to find some signs of dead or alive life?
Yeah, we've done some thinking about this. We actually have been trying to publish like a somewhat longer article eventually that it just keeps getting pushed to the back of the priority list about where life could exist on the solar system, like based on what elements are present. and other issues. Like, I have strong opinions about how impossible it would be to terraform Venus. Titan gets thrown around a lot. The problem is it doesn't have any reducing equivalents. And so while there's a lot of fixed carbon there, there's no oxygen. And not only that, there's nothing that can be used as a source of oxygen or any to do the redox reactions you need for life. So that one's actually very low on my list. Titan is for that reason. Europa is the big one. You have liquid water, and then you probably have everything else you need in those underwater oceans. And so if I were to name the place in the solar system that is most likely to have life, it would be Europa. I know there are plans, and in fact, I'm quite worried about like the contamination of Europa through exploration.
Yeah.
There are these plans to like build a robot that could tunnel through the ice, and they're very worried about contamination there, and I think they should be more worried. Although NASA is usually more worried than they should be. But I don't know. Were there any other ones you wanted to ask about in particular? Those are the ones that stick out.
Yeah, George mentioned Europa, and he mentioned Enceladus, the moon of Saturn. He mentioned specifically the geysers that have gone up and some of the very preliminary assessments of those geysers that spray into the atmosphere. And it was more discussion of what equipment we need or how we would best detect it, which he's worked on in the past. But a big question, if we did find life somewhere else in the solar system, what would that mean to you for the abundance of life elsewhere?
Well, I mean, now you're getting into like the Drake equation. If there's life out there, why haven't we seen it?
Yes.
Which is a really interesting point. I mean, I'm not like a dark forest theorist kind of person. I think that there are some pretty easy physical explanations for why we don't see life everywhere that mostly have to do with how darn big space is and how much signal you'd actually need to hear a signal from anywhere else. And so maybe some combination, like I would be almost a little bit disappointed to find life on another planet in the solar system, because it means that it almost is even harder to do interstellar travel than we expected. But at the same time, it means that we then get to explore a whole other branch of life, or maybe find out that it's forked off of our own at some point, which has some really interesting panspermia implications. So yeah, I mean, it's sort of a very philosophical question, and I kind of like, we'll see what it is and then move from there.
Yeah, if it was DNA based at all, it would be very difficult to prove that it didn't fork off even very early. But if it was truly a second event, it does hint that it's quite abundant, I would think. And you mentioned the dark forest. For those who might not know that reference, Cixin Liu, the three-body problem, essentially their explanation for the Fermi paradox, part of the Drake equation, is that there's intelligent life out there that's essentially hunting and eradicating other life. Very scary possibility there. But I think a rarity, and we just don't know enough of the parameters to the Drake equation to really know. But if you look at life, particularly intelligent life on Earth, it's really just a flash in the pan. The last tiny little layer, are we beginning to produce any signals that we would have any hope of detecting from afar?
And I would love to see an analysis. This probably exists somewhere, but it's like, how good of signal detection would you need on various planets farther and farther away from Earth to detect our signals? Because I bet it's actually really hard.
Yeah.
And that, like, all of our astrophysics of bodies that are light years away are based on suns. So you need signals that are, like, as strong as a star in order to actually communicate across interstellar distances, which we sure aren't generating.
Yeah. They often talk of the first radio waves, the first TV waves, but those aren't detectable outside a certain amount. That's a very interesting calculation. Yeah, so I'm excited that you get to work in this field of advancing astrobiology, and some very exciting points coming up. With the excitement of the Starship and other advances that might take us to Mars one day, are there certain key timelines that you're trying to hit to have these organisms ready?
Yeah, I mean, we talk about flight testing, and a lot of that really does require Starship to be operational. I mean, we'd love to do a flight test on Mars, and we've got a couple different sort of sketches for that as we move forward. We're sort of very ambitiously targeting a 2031 launch window, which would be kind of our first demonstration of ISRU with a couple different options there for how far we get. It's like, do we just grow something on Martian resources? Do we grow something on Martian resources and then make something useful and then purify it? Or do we try to go all the distance and like we sort of have this design that we've scoped out for how you could use biology to create, we're thinking like these kinds of bioplastics or maybe a cellulose aerogel, and then like using 100% Martian resources, so it's technically like you can make an infinite amount of it as long as you just keep running the bioreactor, and then use that to create like a passively heated greenhouse on Mars that can create sort of a habitable environment for life.
And for these first ones, no human's gonna go with them, obviously. So how much robotics or remote control is involved in these first systems that you envision sending up?
Yeah, and this is a big question because obviously it takes like multiple years to flight test anything and to sort of demonstrate it out to the point where you can actually fly it. And so our most basic version would require actually very little additional things. We'd base it a lot off of the Phoenix lander hardware, which had a wet chemistry lab on it, which is where we get a lot of our data. Where what they did is they took a small amount of Martian regolith, they mixed it with some water, and then they used various probes to measure the various solutes that dissolved in that water. And we'd want to add actually something pretty small to that, which is basically, okay, now add some life and some like lyophilized bacteria and some acetic acid. Now does anything grow? Because our simulations and our, in fact, test media says that it would. And we're engineering organisms to be better at growing and being more productive in those conditions.
One thing I love about what you're doing is the open source, open presentation of all your data. I was very excited to see your ISRU, the regolith experiments. You publish it. You have blog posts. Could you describe a little bit your communication philosophy at the company and how that influences your science?
Yeah, I mean, we try to be fairly fast cycle time. Like, if we make a discovery, we kind of want to write it up internally so that we can think about it, we can keep track of it. But then it doesn't make sense to go through like a multi-year publication process every time. That takes an enormous amount of time, and it means that it's much slower to communicate things to other people, and it kind of makes everybody's science move an order of magnitude slower for such a long process, which takes so much effort. So we're trying to do these much faster sort of blog post style updates that don't contain all of the detail necessary, but are like updating people on our progress and sort of encouraging open dialogues where if somebody really wants to know, they can ask us. And then we are also planning these like larger sort of publication style articles that kind of go into a lot of details. We've got a couple of those in prep right now. But in the meantime, these blog posts, just, 1,500, 2,000 words as like a, hey, this is an experiment we did. Here's what we learned from it. Can be a really valuable way for us to both crystallize our thinking and also share everything without making us wait like a year or two for a full publication or the full peer review process.
Excellent. And for digging in a little bit more to in situ resource utilization, who have you talked to get an idea of what's going to be needed there? Like partly making things for rocket fuel or other applications, or mostly focused on human habitation needs while you're there?
We've talked to a number of people. I mean, we have a good number of contacts in sort of the space community, as well as various others. We did our second, last year we did a Mars terraforming workshop. This year it was called the Green Mars Workshop, which we published some details on the proceedings from last year, and this year there was sort of a summary that went out. Which had a lot of people from those various communities in that. And we kind of talked about ISRU. Right now, we're sort of focused on the products that would be more practically achievable, and also that biology is good at. Rocket fuel is very high energy. Biology is not necessarily good at creating very high energy products. It's very good at, what it's really good at is self-propagation, right? Like that's the superpower, is it can make more of itself. And it can also do some pretty subtle, interesting chemistries. But I don't think rocket fuel is the right approach. What we're focused on more now are some like basic building materials. We'd love to be able to make a sort of insulator of some kind. We're thinking either we make a mixed PHA PLA plastic that you could 3D print in patterns, like a grid pattern with voids in it that would serve as a good transparent insulator, or we make a cellulose layer aerogel, which you basically just make a cellulose layer, and then you can expose it to very low pressure, basically the Martian atmosphere, and all of the water will evaporate from it and make an aerogel that is both transparent and fairly insulating. And we are targeting those as sort of our two most material properties. We investigated a whole bunch of others. We looked at rubbers, we looked at cements, and those are kind of much harder or like much less efficient, so much so that it's like basically would be an entire company to optimize those to the point of usability. The other things are, of course, like more human-focused resources. Food is one option, but I'm actually more interested in making remediated soil. So Martian, regolith Martian, it can't grow plants. The Martian was published, as much as I love it, it was published shortly before we discovered that there's high levels of perchlorate on Mars. And perchlorate, of course, is a toxin. The levels it's at probably kills plants unless it's a very rich soil. And also it would be very bad for humans. It kind of kills your thyroid glands at low concentrations. And so I'm doing experiments now trying to remediate out that perchlorate biologically. We do that now in sites where people made a lot of explosives, and perchlorate's a component of a lot of explosives, where there's a lot of perchlorate contamination in the ground. And there are all these bacteria that have sprung up that are good at reducing it, kind of using it as an oxygen source. So there's this whole potential process where you like put in soil, you put in a carbon source, maybe you do it photosynthetically with carbon dioxide, and then you use perchlorate as your oxygen source to make an efficient metabolism. And that gets rid of the perchlorate, and maybe your output from there is biomass and then remediated dirt that you can use to grow plants. But we actually are kind of like, a lot of the components of soil now are or is organic matter. And so one of our second tier products that we're very excited about is your input is Martian dirt, water, and then some sort of carbon source, and your output is soil, which has organic matter, it's got all perchlorate remediated, and it's ready to grow plants. But you would need that sort of process before you could actually grow plants with soil that's present, or the rock that's currently present on Mars. There's a couple other various products. One of the interesting things which we're having trouble convincing some people at NASA about, but when you do the math, it's obvious, is that there's a big hubbub about vitamins. It's like, oh no, all of these vitamins that you take to space have short half-lives. So if you go on a 3-year mission, you need some way to make vitamin C while you're up there because your vitamin C won't last that long. And then the astronauts will get like these debilitating nutrient deficiencies. And that's not true at all, because the experiments that measured those were measuring the levels of vitamin C in wet food. Like they basically like gamma sterilized like a lasagna. And then after 2 years stored at, room temperature, yes, the vitamin C in that lasagna degrades. But if you have a vitamin C tablet that's powdered and dried, you lose like almost none of it after the same time period. So basically, to deal with that issue, all you need to do is bring multivitamins. You don't need to make all your nutrients in space.
But to become ultimately self-sustaining, you'd want that capability eventually.
Yeah, but if you're making food, you're going to want something that's fairly well-rounded, and especially even if you're using like a yeast or some other organism to make a nutrient paste, those organisms are very easy to engineer to make those things. Mm-hmm. But I would say, so like the harder part is actually making the food in the first place, not making it nutritionally complete.
Mm-hmm. Yeah, I agree.
If you can make the process, you can make it like serve your nutritional needs.
And you mentioned one of the great challenges, the perchlorate in the soil. What other unique constraints are there on Mars that limit biological growth for your purposes?
I mean, there's a couple different regimes we're talking about. Like, if you're growing stuff indoors, all of these flight tests I was talking about, you'd have like a big steel tank that you try to grow stuff in, right? And so there, it's just kind of the chemistry, right? It's the perchlorates in the rock. It's where do you get the water? It's how does your electrolytic setup work that turns the carbon dioxide in the atmosphere into a carbon source? Or do you try to use photosynthesis, which would require a big surface area for anywhere near the same amount? It's actually more efficient per surface area to use solar panels to use electricity to turn carbon dioxide into acetate and then feed that to your bioreactor than it is to just use the same amount of surface area as a photobioreactor where you're growing cyanobacteria, which is part of why we're in on the acetate train. But I would say that then when you start moving outside, I wrote, this was actually one of my early blog posts, was like, why nothing can grow on Mars? And the answer is mostly water. A lot of the chemistry is doable, but because Mars is below the triple point, all of the water is frozen, and the stuff that isn't, which you may have heard about, these like eutectic brines, is so nasty, it's so dry It's closer to think of those like silica gel packets they put in beef jerky to dry them out. Those liquid patches of liquid water are drier than that by like how much water is available because there's so much salt in it.
Yeah,
And
that's not
so I
very
would
usable.
consider that the big challenge in a lot of ways, is where you get the water. There's actually quite a bit of water on Mars. It's enough that if you melted it all, you'd get a layer about 100 feet thick over the entire planet. So not as much as Earth, but like still a pretty good amount. In contrast to Venus, which if you did the same thing, you'd get like a couple millimeters. I think it's like 4 or 5 millimeters of water over the entire surface of the planet. All the water is just gone. So the water is there. It's mostly in the polar caps or in the subsurface mid-latitudes. So there's these areas like 40 degrees north, where like there's probably some regolith, and then just underneath that regolith, there's a lot of permafrost, where you could get ice out of. Those are, I'd say, the primary issues: the perchlorate and the water.
And one big distinction from talking with you is microbes that would be used inside the facility, indoor organisms, which you can control the pressure, you can control the temperature, and it's obviously a much bigger leap to have anything that would survive outside in the harsh temperatures and pressures. Where are you putting your effort towards those two goals?
Yeah, I mean, it's split. Like, we're obviously further along on the easier goal. We can kind of simulate these indoor scenarios where the only challenges you're facing are from all of your nutrients coming from Mars and not the conditions of Mars. We're doing a lot of simulations. I've been mentioning these, like, let's make a passive greenhouse. We've been doing a lot of simulations there in collaboration with some climate scientists, for Martian planetary scientists, to sort of figure out, like, okay, if we had an incubator of these properties, or sorry, an insulator with these properties, this insulative capabilities and these transmitivities, could we like put it down on one of these permafrost areas, and then over the course of like a couple years, it would heat up the regolith enough so that actually it would be habitable. Like, you'd have liquid water, and the temperatures would be above freezing most of the time. And how much of the time, and how does it freeze thaw every day? And these are the sorts of questions we're thinking about. So we think that the first environments it would grow outside, and I'm using quotes on that because it's not really outside. We're kind of artificially making things more favorable. There's a lot of other issues that may need to be pressurized, it may not. The low pressures of Mars aren't actually necessarily a problem for bacteria. There are bacteria that can grow just fine in that level of pressure. The problem is that you lose your water fairly quickly. So if you like slap this big insulator down and it like melted this big area of permafrost and you had bacteria growing in it, all of the water would evaporate over the course of months to years. We actually need to do that math. And then sure, you'd make some biomass and be in your soil, but like all the water left. But then if you like stake down the edges and make it a pressurized area, then you need to make it a lot tougher so it doesn't explode. And the thermal properties change. There are these really big temperature swings on Mars. There are areas that go above freezing, but it's like 80 degrees Celsius temperature swings between day and night. And one of our big worries was that these insulated areas would have similar temperature swings. So far, we don't see that, but the math might change if we include that much water vapor underneath them. And so we're kind of thinking these sort of areas, and these areas might get pretty big. I mean, people have these dreams of like giant domed cities on Mars. I don't think that's necessarily unreasonable if you're making all of those materials locally. But that would be a much easier thing to do than to terraform the whole planet. The planets are very, very large, and so while heating wouldn't necessarily be that big of a problem, oxygenation and sort of full planetary chemical modification are. And so assuming a fairly productive amount of biology, you would need like a year or two to fully oxygenate like a 100 or a 200 meter dome, which isn't too bad with biology. But to fully oxygenate the planet, you'd need like 10,000 years or so. And that number is pretty hard to get around. You just need on the order of like 10 to the 11th kilograms of oxygen. And the only way you make that is with a full planetary biosphere, and it still takes 10,000 years.
Yeah, I think clearly it'll be these small pockets that come first. What do you envision as some of the first Mars settlements or colonies, even temporary? You assessed above ground domes. Obviously, there's volcanic vents or underground. What do you think is the most likely or suitable with current technology or near future technology?
Yeah, I mean, I'm not thinking all of this will come super soon. We actually went over this in some detail in the Green Mars workshop, and sort of in the summary to that piece, we have some description of this, where it's sort of three big phases. The first is very much outposts, and I think that'll be true for a long time. Where at first you have very temporary habitation, and then it gets sort of longer and longer. But really, it's very hard to fully be permanently settled on Mars because of just like the tech stack and how much you would need to make locally. Starship might make it so you don't need to make microchips locally, but all of the food and medicines and other sort of larger bulk items you would need to do locally, and that's quite challenging once you get into the math of it. So I think that for the near future, there won't be permanent habitation. I don't know exactly what design would work well for like the first permanent settlements. It'll probably be in a lava tube or dug underground in some ways. The radiation is a whole issue we've dived fairly deeply into, and it's not as bad as interstellar space, certainly, but until you get a little bit more atmosphere in there, it's pretty challenging. So those will be the first things, and then you'll have the sort of more domes and dome craters and other things like that later on. But those are very much like once you have something there already and sort of self-growing biological solutions to these ISRU issues, you can sort of create something that large.
And one thing that came up with the conversation with George was the importance of self-sustaining biospheres. Obviously, there was the Biosphere project on Earth. Not sure if you dug into that or how it ended, but lots of unexpected things happened. Interactions between the life. That one ultimately failed because the concrete absorbed a lot of the oxygen, changed the pH in the ocean, and is this something that Pioneer Labs is working on, how to have some self-sustaining, or is it more directed towards specific applications of biomanufacturing?
We're thinking about it. We kind of have one self-sustaining biosystem that works, and it's called the Earth. Smaller systems are hard to balance and hard to build out. I would say this is like a field of science that we don't understand yet. And we're not, it's sort of like people always ask us if we're going into communities. Communities in biology are how everything gets done at the bacterial scale. But like as a field, like bioengineering does not understand how to engineer them. And we decided that is a very interesting topic and probably an important one, but not one that we can solve on our own. And so we are kind of more focused on these specific bioprocesses that we can make, and maybe like we can make a we are not for profit, and what that allows us to do is focus on these chassis organisms and be like, here's a P. putida strain that if given these Martian inputs that are entirely sourced from Mars, it will grow up to this biomass in this time. Then you can engineer that in all of the ways that people are already engineering it to create all sorts of interesting bioproducts, various chemicals that are very valuable for various things, or even things like food or this bioremediation approaches that then can kind of kickstart the sort of Mars in situ resource utilization technology. But yeah, creating a full biosphere is very hard, and making it stable probably requires scale. Everything we've seen, like it would need to be big. And so this is part of why one of our big focuses is like, can we make this transparent insulator entirely from materials on Mars so that you could just scale it to something large?
Yeah, got to make the space. Shifting gears a little bit, I wanted to get into something I know is dear to your heart and mind, is influence of science fiction on your thinking, your motivation, and in particular Mars. It has been in some of the most early science fiction writing. It's inspired hearts and minds throughout the years. Wonder if you want to share one of your favorite books or authors or inspirations to end up in this field.
Oh, I mean, it's got to be the Red Mars trilogy, right?
Yeah.
I mean, I've read a lot of science fiction, and there are various things I really enjoy about different genres. But in terms of Mars, I just don't think anything is quite as good. It's fairly solid science. There's a couple issues he didn't know about perchlorates. He overestimated the impact of dropping comets. But like, it's such a good exploration of the kind of time scale and cultural differences or changes that would need to happen. That I just love that series. I mean, I think I remember you recommending it to me way back in the day.
I did, but when you were with me in graduate school, rotating with
Yeah.
me, I recommended it. It's an excellent series. For all who haven't read it, Kim Stanley Robinson's Red Mars trilogy, Red Mars, Green Mars, Blue Mars, the exact
Yep.
order.
Yep.
But excellent series that gets into first the journey out there to set the first colony, and then they enable them to live longer through some therapies, but it shows some colonization, breaking free from Earth to some extent, and a lot of the technologies that eventually get microbes on Mars and make a sustainable, breathable atmosphere, which I think he has a quite accelerated timeline, but excellent, well written, especially into the geology of Mars, the descriptions of the landscapes. It was very, very well researched, and he certainly took some scientific leaps. But I think the audience would enjoy that.
Yeah, and then The Martian is also fabulous. I mean, I read that when it was still self-published before it got picked up by a publisher, and then saw the movie. And I just it's a very good representation of sort of science being fun and interesting and a lens to look at the world through, which is not always common. It's kind of a way how to think with science in the context of Mars, which I really enjoy. That's the kind of sort of science communication and representation we need more of, almost.
Yeah, and it's amazing to see that an early generation with going to the moon and the first human space program was motivated by that. And many ask, why haven't we gone since then? And it's very exciting that there are now projects with the US and other countries aiming again for human space travel. How do you think this will inspire the next generation?
I mean, I think it's quite complicated. Like, you're getting very deep into the politics behind the space race and sort of modern geopolitical systems. And I think that's something I'm not quite able to talk about. I certainly know a number of sort of the space community people who are very excited about all this and do work to kind of try to popularize Mars in the public eye to sort of set up for the next generation of space exploration. But I don't know what the right approaches are or what will end up happening. I really think of my science as a great way to explore what's possible, but I don't know all of the steps necessary to take that to fruition because you're really getting into what moves governments, which is a pretty hard question in and of itself.
Yeah, quite out of our normal wheelhouse. But one thing I think you do an excellent job of is testing some of those things. Like you said, drop-in comet, they overestimated it. I think you and Pioneer Labs have done a great job of analyzing the chemistry, the physics of the environment, and really taken some of these abstract ideas and tested, okay, is this actually possible? Are there any other science fiction-inspired ideas that you are working on, or does your inspiration come more from the actual physical research now?
I mean, one of the really interesting things in all of this has been figuring out where science fiction was right and where it's not. Because there's sort of this public conception, and maybe I shouldn't say public, but it's like among scientists we talk to. It's like, we say, oh, terraforming Mars, what would that look like? And they're really informed by things like the Red Mars trilogy.
Yeah.
And in our own thinking, it's been quite interesting to realize like what elements are harder and what elements are easier. For example, like I said earlier, kind of offhandedly, that heating Mars might not be that challenging, because you just need to play with the greenhouse characteristics. And there's been some math done on how much greenhouse gases you'd need to warm Mars up, and it's actually quite a lot. You'd need more fluorine than exists in the top 100 meters of the Mars regolith in order to make enough greenhouse gases to warm the planet up so that it was mostly above freezing. But one of our collaborators, Edwin Kite, is a professor at the University of Chicago, has figured out this design for these nanoparticle aerosols or maybe these graphene-based aerosols. He sort of has a couple different designs, all of which should work, which, if suspended in the atmosphere, would actually do an amazing greenhouse effect. And so you could theoretically have one factory. Sure, it would be like a very big factory, but it's like the size of factories that exist on Earth. And that could produce enough of these nanoparticle aerosols to completely warm the planet. And like the math on that is maybe not set in stone, but it's like looking pretty favorable.
And that's
And
carbon
so if
based? You said it's graphene based?
there are a couple options. One is a metal-based rods that are like 10 micrometers long by 100 nanometers wide, and then the other is sort of these graphene patches that are like you just need some conductive surface area on those, I think. And yeah, they're very light. You would just suspend them in the atmosphere, and they'd warm the planet up in like a couple of years.
And this goes back to a concept in the Mars trilogy. There was a group that felt we shouldn't change Mars. I believe they were called the Red Martians. And how do you feel about humans' obligations or ethical concerns to maintain what's already there? I guess in my mind it depends, is there life or not? But if Mars is desolate, there's no signs of life, do you think there's any obligation to maintain? Because clearly this experiment will radically change Mars.
No, I do. I do actually think that. I mean, it is a place that has its own kind of natural beauty. And when people say terraforming, they mean like Earth. But as you explore more and more, you realize that we're not going to turn into Earth. We're never going to make the atmosphere of Mars as dense as Earth's is. There are always going to be high altitude areas of Mars that are really never going to see liquid water. I'm thinking some of the high mountains, some of the poles, that'll probably remain very dry and very desolate, even if we can make a significant amount of the surface livable. And so I don't say it'll take care of itself. There definitely needs to be some thought given to maintaining some parts of Mars as sort of nature preserves of some kind. And I wouldn't even say that the presence of life necessarily obligates you to like not touch the planet. We definitely want to study any life that's present, and we definitely don't want to destroy it entirely, but it just kind of it's data that shifts how you think about these ethical implications. And there's a lot of thinking there to do. There's some books in that space that we're certainly paying attention to, and dialogue in the space community is about like what is our role in shaping the spread of life throughout the solar system. Do we kind of have the is it what's right? And I think for now, with our technology where it currently stands, effectively all signs are pointing the same direction. All of this ISRU technology we're developing, even for some growing stuff outside, before you terraform the planet, if you just want to have scientific outposts that study things, you're going to want the same technology. And so we've certainly talked to a lot of people who are much, much less favorable on terraforming, but they're still very excited about the science. They still want to explore Mars. They still want to have humans on Mars. They just want to be careful about where those humans go and have those humans able to find life if it's there and study it. But regardless of whether that life is present or not, we need to think about what Mars's end state will be and not just go for the goal of making it the same as Earth. Because it's not going to be Earth. It's going to be something different. And thinking hard about exactly what that is very much a part of the terraforming journey. But before we know what's possible, it's hard to sort of state your end goal philosophy.
Yeah, interesting discussion on terraforming. And there's some thoughts about, especially even in these books, about bioforming or changing us to fit Mars. In the Mars series, they have some natural adaptations of certain people, if you recall, could tolerate temperature much lower, generate their own heat at a higher capacity. To what extent do you think about or plan that we might, obviously technologically, we need suits, we need materials, but do you envision us biologically changing ourselves to better fit Mars or other places?
Yeah, totally. And there's a couple easy ways. I mean, our end goal Mars that is sort of achievable with current technology has quite a thin atmosphere that's mostly oxygen based, but not so dense not so thick that it would be very flammable. It's a similar level of oxygen to what the Apollo astronauts breathed, or that exists, 2/3 or 3/4 of the way up Mount Everest. And so you'd probably, native humans could survive it. It would just be challenging, and over time they'd develop like bigger lung capacity and stuff. But I could see engineering that sort of a better oxygen uptake into people, or better tolerance of thinner atmospheres. Similarly, and probably a bigger issue, is radiation. Most of the radiation that gets through to Mars is ultraviolet. You actually do not need, like, even the present atmosphere absorbs a lot of the solar particle events and the galactic cosmic radiation. But it is enough that you don't want to spend more than a year or 3 going to or on Mars. Like, a lot of the problem is actually like the time it takes to get to Mars. You're pretty exposed to these galactic cosmic rays. But on Mars, modern humans would not do well over the course of a couple of years unshielded, which is why people talk about being underground. And a thickening atmosphere could mostly deal with that. You need to raise it by about an order of magnitude, or about 2 orders of magnitude, about 100-fold. But that would, again, take millennia, and a much simpler and easier version would be to engineer people to be more radiation resistant. And I think that's like a pretty critical one. And also, it dovetails well with like cancer. Like, avoid cancer by suppressing and having better mutational repair systems. We know how those systems work in biology. I would not be surprised if this comes along kind of as a side effect of people figuring out better ways to engineer people to resist cancer or other kinds of mutation sources. Or aging, because random mutation is definitely playing a role in aging, as we both know. So some of those things I think are pretty obvious. Others are a little bit less so, like the low oxygen. The temperature one doesn't seem too big of a challenge for me. Like, it's easier to put on a coat than to make yourself produce enough heat, or like grow thick enough skin to not need one. And also it means that then you could go inside and enjoy things, or go to a different place that is more comfortable. So I don't know about that one. That's sort of a more physics-based one. But the radiation resistance and the lower oxygen, I think, are more likely.
Yeah, and if we do establish these colonies and eventually have babies born on Mars, there's been a lot of speculation of what they might look like taller because of the less gravity, weaker heart, different adaptations. Have you done any thinking of what human reproduction might look like on Mars and the challenges?
Well, I mean, I think that gets at a really interesting point. I don't know if you've seen A City on Mars, the book by, which were they? The cartoonists. It was a really good book, because it pointed out, it was a great example of, like, when I said earlier, like, what do you need for society? You need so many things. You need the ability for people to give birth. We have no idea what giving birth would look like. Birth is tailored for one gravity, and actually thinking about the logistical challenge of making that happen on Mars is really difficult. And so I'm sure there would be natural adaptations. I'm sure they would have bigger lung capacities. I'm sure they would probably be taller. But, like, this is part and parcel of, like, this whole suite of medical understandings that we do not have, and we don't even have the capability to start gathering data until we can have humans on Mars for extended periods of time. So this is, like, very much like the next phase is like, okay, humans are on Mars in outposts. Let's gather some data. Let's try all these things. And I don't even know what those experiments would look like. But we are working on designing those outposts now, I think, or at least understanding how they would possibly sustain themselves. But, like, I don't expect to know that answer in my lifetime, to be honest, depending on how the aging research turns out. But it's sort of like there are so many things upstream of that it's hard to speculate on, and we need to do the science carefully, and the time to do that science is not now.
Yeah, definitely need that support structure, and if anything goes wrong, you're 2 years away from a resupply mission, 2-year windows. That's quite difficult to have that society. So moving on, one other part of your life is that you're an author. You've always been interested in science fiction. We've had great discussions, but more recently you've been a published fantasy author. I wonder if you could just describe what are the differences in communication style for pure science writing in academia versus what you do now, more open, rapid communication, and in fantasy to a broader audience.
Yeah, it's been really interesting writing that story. Human brains focus on narrative, right? like this is kind of what we're built to do, is like understand a narrative. So we always talk about in science writing, like you want to make your science into a story people can understand. And I've definitely kind of explored like you don't need to not just make a narrative, you need to make people care about that narrative. And if there are characters they can attach to, that gets a lot easier. And so in a lot of senses, science communication is working on hard mode because you're working with abstract concepts. You can't make people feel inherently attached to a character. And so it gets much easier to sort of talk about these things when there's like a person that you feel like you know talking about them. So, you know, in my story, I go into a lot of these scientific concepts and I get to sort of expound on some science that I think is cool to talk about. And it's so much easier to communicate it because there's sort of this emotional connection you can draw on. But then when you're trying to write like a science communication piece or a article itself, you're kind of trying to explain things completely and fully and concisely without that emotional connection, which is much harder. And so we've kind of developed and worked on our style over time. I've done some writing fellowships and such to learn how to do this better. But I would say there's a lot of tricks. You need a very solid narrative. You need to not waste people's time. One concept we like talking about is we like to make our pieces scale invariant. So you can stop reading at almost any point and still take away a full idea. So like there's the title, and if you read the title, you'll understand what the piece is about. And if you read the introduction, you'll understand more about what the piece is about and usually get our big takeaway. So like actually you could just read our introduction and be like set and know everything. And then if you read more, you'll get more and more detail. And it's very hard to properly communicate things, but it's like the way that science happens is by doing this. And so I think a lot about when I write scientifically or technically, I'm like communicating very clearly and directly the core ideas, but it's to a relatively small set of people. And it, like, I know that, yeah, only 100 people are going to read this, and it's 100 people who need to read this, and that's fine. But when I write, like, my fantasy series, then 10,000 or closer to 25,000 these days will read it. And so if I can put in this interesting idea about science, like, I may not be going into as much detail, I may not be justifying it quite as well, but I actually have, like, a broader impact on the scientific consensus, in a way. And I don't know, I think about that sometimes. I'm like, if I really wanted to shift public opinion on these things, maybe doing science and writing about it isn't the best approach. But I love it, so here we are.
And one thing I've always noticed that you have a great talent to distill complex ideas and really write deeply about a thing. I know you went to conferences and you write this complete summary of all the talks you saw and how it went together. And that's a great skill of yours. And how are you implementing that into, I think it manifests in the writings you've done for Pioneer Labs, but how do you think of using that skill for what you're doing now?
Yeah, I mean, if anything, what we try to do is teach that. We have a very detailed sort of lab notebook system where everybody writes very good summaries of their experiments and sort of like pre-sketches out blog posts almost to help us communicate with each other. I would say that like science communication is king, and that includes between scientists, and it includes even between people in the same lab. Well, one of my criticisms of academia is that in an academic lab setting, you often are like the only person on your project, and you're sort of the master of it in many senses. So you don't usually need to communicate it super well, and lab meetings are not the best format. I think people need to practice communication asynchronously through writing more than they do. And when you're in a more industrial setting, or like we're basically modeling our structure off of a startup biotech company, you really need to be able to communicate findings across the company, like quickly, efficiently, in detail, without missing important parts, but also without spending an enormous amount of time on it yourself. If it takes you a week to write up a week's worth of experiments, you've just doubled how long it takes to do science. So you need to be able to like very quickly distill out the important parts and then pass those along to everybody else without it taking too much time. And I think doing those notes is something that I actually am really glad I did, because it was very much like I was distilling the information from a talk as the talk was happening. And so I would say there's an enormous amount of information that's present kind of internally that we then distill again, and that's already quite distilled from like experiments, that then gets distilled again into those Substack posts. I'm actually very curious to see if it would be possible to unleash, we've got like almost 1 million words or so of writing in sort of the Pioneer Labs databases. And if you could like unleash an LLM on it and be like, ask all these questions to help understand it. I think all these people doing AI for science, it would be very cool if you could point it at a giant corpus of data like this or writing like this and then get out interesting syntheses. Sort of like, instead of training on literature, training on lab notebooks. But they have to be good lab notebooks.
Excellent. That was a great segue to my next. I was going to ask, what, if any, application of AI or LLMs are you using at Pioneer Labs?
If you're not using AI in this day and age, then you're leaving productivity on the table. We've been using them for various points. I mean, for some of the writing, I have to caution people who are starting writing about using AI. Because the purpose of writing is thinking. If you're not thinking, then you're not writing well. And if you're offloading that thinking to the AI, then you are doing yourself and your readers a disservice, because the AI is not going to be able to magically parse the things you want to say out of the ether. So it is very good at kind of removing the drudgery of stringing words together. But you need to tell it exactly what kind of message you want to give. I would say, if anything, it's gotten easier to just like write something very badly and tell the AI to clean it up. I will have fragmented sentences, I'll have disjointed thoughts, and I'll just be like, here's a thing, it's twice as long as it needs to be, I didn't put a lot of, like, all the thoughts are there, but the writing is not. Make it good writing, and it'll just do that. But you need to do that thinking yourself, and that's the hard part. And it's very easy for people to offload the thinking to the AI, which can be very much of a trap. I would say, in terms of AI for science, I mean, Erica De Benedictis is my co-founder, and her husband is Sam Rodriguez, who is one of the founders of Future House, and they just spun out, I forget what they call it. I think they call it Edison? I'm not exactly sure the name. But they are an AI for science. Future House is an AI for science nonprofit. It's one of these focused research organizations. And they have some really cool tools that are basically literature searches. I know some other people have their own like ways to do like deep research and such, but both because of our connection and because we've had access for a long time, I will still use the Future House tools to write up research reports or do answer questions. They have this wonderful tool that used to be called Crow, I forget what it's called now, which is basically like, has anyone ever done this experiment? And then it'll just like find it to you and answer the question. So the AIs are a great tool for that. There's also some other applications. I don't mean to turn this into an advertisement for them or anything, but they've got a model where you can give it a very large data set and ask it to like gaze into the data and find any patterns. And I would say that it's got about a 50% hit rate, which means like it'll look at them and it'll find interesting stuff, but then you got to look very closely yourself and be like, all right, is this actually real? And a lot of the times it is. And it's actually, we've had some very large data sets that we pointed it at and been like, do you see anything here? And we've already analyzed these and we've already found meaning. And then it finds new things we didn't see. And like, it found the thing we already found and it found 3 other things. And 2 of those were wrong, but one of them was right. And it was something we hadn't seen already. And so I'm very excited for like the up and coming age of like data interpretation, because especially in the field we're in, which is like gathering very large data sets on what kind of engineering to do and sort of evolutionary style horizontal gene transfer, there's going to be a lot of signal in that data that is hard to parse out from the noise. And it can be very tempting to find something and then put away the data set. But if you can then point an AI at it and be like, is there anything else in here? That might be a great way to kind of actually get the full return that's possible. So there's a lot of different angles in which I think AI is changing science. I'm not one of these people who's like, oh, it'll entirely replace scientists, because I don't think that's true. But I do think that it will really sharpen the tools. It'll be a new tool that will help scientists do a lot of new things.
Yeah, exciting applications that I do think humanity as a whole, might have certain blind spots that new approach might point us out. And like you say, incorrect or hallucinations, this is a common feature, both for writing and for science. You really need to not be just putting out AI slop. You need to be checking it at each point, but you're right, you're leaving productivity on the table if you don't use it. And how do
Or
you
just
empower
the
it?
time. Like these reports would have taken somebody like 50 hours, and like right now it was the output of like a second year excitable grad student. But like it'll get better, and then it'll have a higher hit rate, and I'm looking forward to that time. Anyway, sorry to interrupt. Keep going.
Yeah, yeah. And one last question, I think we're up on time here, but how do you see these tools influencing evolution? The Arc Institute came out with genome evolution for the most simple viruses. Where do you see generative AI to help you evolve these organisms in the future?
Yeah, this is. I've got so many thoughts here. One of the things I think that the genome models are missing is any tie-in to function. They're able to discover genes on their own, for example, but they're not able to really have any input on how those genes work and what they're doing. They kind of just know, oh, these exist. Great, good to know. One of the things we're really trying to do is these very large-scale functional genomics, where we like take a large number of genomes, like 1,000 genomes, fragment the DNA, throw them into libraries, barcode everything, insert them into new organisms, and run them in stressful conditions. And maybe those are Mars conditions to help us make better organisms, but they could also be other conditions. And then with a lot of sequencing, we can get the fitness of every one of those fragments, of every one of those genes, or every one of those organisms. And that can actually provide you with like a phenotypic fingerprint on this crazy amount of existing data that exists. And so this is kind of us moving, it's like very parallel to our Mars engineering. But I think that that kind of feedback on the real world, that's not just like this sequence exists in biology. There are a lot of sequences in the human genome that don't do anything. There's a lot of sequences that even look like protein coding stuff that don't do anything. And I think that it's going to be very hard for AIs to learn things that are more complicated than viruses. Because viruses are like super compact and functional, right? And I'm sure they'll get somewhere, but I really think that having an extra level of detail on the data that's like basically an annotation of what regions do what at like a gene level or a gene level is going to be really critical for moving into the stage where you can actually design organisms and have them work.
And I think that's one of the grand challenges of the Human Genome Project. And looking at it, they expected more genes, more exons. But that non-coding, large intronic space with multiple splice forms, it's really one of the... There are other organisms that have it, but humans have a very complex assortment and variety of the expressions of genes. And you're right, that's very... They called it junk DNA, or dark matter of the genome, and... There's a lot of breakthroughs. There have been a lot of breakthroughs already, but our understanding is still very limited of the true function of all of that.
I mean, I've got my own hypotheses. I'm pretty sure a lot of that is evolvability adaptations to allow humans to continue evolving quickly. You get genes popping out of those, orphan genes they're called, every so often. So it's kind of the like genomic junk pile where stuff is free to drift. But if we wanted to get, I've got a blog post out on that from a couple years ago. If we wanted to get into that, we might have to do a whole other podcast episode.
Yeah, I'd love to have you back on. But Devin, thank you so much for joining. Great conversation today about Pioneer Labs, evolvability, and the future of biology in space. Thanks again, and love to have you back on later.
Cheers. Thanks,
Bye.
Corey.